Binhang Yuan, who's going to be talking about a new objective automatic computation framework for evaluating and visualizing
plastic surgery.
Plastic surgery, yes. Sorry, it's cut off on the brochure. Okay.
Yeah, let me see my own. Okay. Okay.
Okay.
Okay. Hello, everyone. My name is Binhang Yuan. I am a PhD student in Rice University Computer Science Department. I'm working with Professor Goldman, and I want to note that this is a joint work between my advisor and Dr. Khechoyan from Baylor Medical School. So here are some examples of the different kinds of head deformity. Like you see, there's lots of seam in the baby's head. So this in different age of the baby, so this key is going to be closed. But if they're closed a little bit earlier, then there's going to be some problem, lots of problems. So when this is the case, the doctor needs to fix all of the problems. And what we are trying to do is we're trying to measurement how the surgery is done, and that was totally objective and automatically. So here is an example. So this baby was diagnosed as sagitty, which means here is this case. So that means this seal closed earlier than expected. So you can see there's a bulging in this baby's head. And yeah, let's see another example. So in this case, the baby was diagnosed as unichronal, which is this case. And you can see one side of this thing closed earlier than expected. So you can see the baby's head is not symmetrical, and we can see this part is larger than this part. So yeah, because this thing closed earlier, so the head has to grow to another direction, and that's the cause of this kind of problem. So let's see another example. So for this baby, it's diagnosed as mortopic. That means this seam closed earlier than expected. So the front head it looks like a kind of triangle. So the problem, so this two-dimensional image show us we are trying to see this problem from this two-dimensional image, but the problem is that we have this two-dimensional image, and the position of the camera is just in the right front side of this baby. So we cannot tell if the front side is normal or not. So this explains why we need better measurement, and we need some higher technology for this kind of problem. So the problem of currently evaluation of plastic surgery is that the evaluation system is based on some wrong observation, and you can see from this image you cannot tell what's wrong with this baby. And another problem is that even the doctors about the surgery are not the same, so they have different opinions about the same surgery. So what we are trying to do is that we are going to provide an objective evaluation system. So luckily we have this 3D medical image system, and this provides us with very good input data for this kind of research. So we can, in this case, we can gather entire head surface of the baby and generate a kind of computer model that we can use for further analyze. So yeah, this image just is a kind of illustration of how the photo was taken. So when we have, you can imagine a baby is sitting here. It's sitting here, and all of the 6 cameras are around this baby. And we can take the photo of this baby, and then it takes a while for the machine to generate the 3-dimensional mesh of the baby's head. Actually, by the way, the triangle mesh is how we represent shape in computer graphics. So yeah. And another thing I want to mention is that for this system, taking this kind of 3-dimensional photo is much less it's less harmful than to use the CT scan. So there's no radiation, so which is very good because the baby is very sensitive. And okay, so I'll just introduce our contribution. So in this paper, we have two main contributions. So firstly, we present a kind of objective computational framework to evaluate and visualize the infinite cranial surgery. And secondly, we select some local features, three-dimensional surface local features from differential geometry to add the doctor to evaluate the local deformity. And naturally, we just include these local features into our framework. And before I introduce our own framework, I'll give a brief introduction for some previously research. So you can see. So for this guy, they just do some analysis on the two-dimensional curvature and on the specific cartoon plan of the baby's head. But for our approach, we consider three-dimensional curvature, and we'll talk about this later. And for this guy, they just consider the normal vectors for head shape analysis, and we also include normal vectors, but in a more accurate way. And for this guy, yeah, they just use a kind of machine learning approach to solve this problem. I think this, to some things, it makes sense, but the problem is that they use the doctor's opinion as the input as the kind of ground truth to mark each patient. And the problem we are trying to overcome is that we cannot let the subjective opinion to change our measurement. So that's a kind of problem. And our system is totally automatically and objective. We don't depend on this kind of input. And for this tool, they tries to generate a kind of normal template for the baby's head. I think this is very useful, and we may include this. But currently, they're just doing some kinds of physical bar to try to aid the surgery. And we're going to consider this in the future. So let me talk about our framework. So our framework contains 4 parts. The first part is mesh simplification. You can think mesh actually means surface in differential geometry. So the second step is going to do the registration, and the third step is local feature computation, and then finally we're going to visualize this result. So notice that we need to do this mesh simplification, or we can say surface simplification, because the input data of this of the baby's head, there's too many points there. So actually this is very inconvenient and inefficient to do analyze on such kind of surface. So we need this mesh simplification process. And now this is the result of mesh simplification. And the left side is the input mesh, while the right side is the output surface. So this just tries to illustrate that we keep the mesh simplification method still keeps the shape of the surface quite well. And the general idea about mesh simplification is that we try to get rid of some of the points on the surface, but we still try to keep the shape as good as possible. And to implement the mesh simplification, we use the classic quadratic error metric dissemination method, which is introduced in this paper. And if you want more details, you can see this reference. And I want to mention the mesh simplification method is quite efficient for our framework. It's only take a couple of seconds to generate this simplified surface. And the next step in our framework is to do the registration. So the purpose of registration is that for each point on the pre-surgery surface, we want to know exactly which point on the post-surgery this point should be mapped to. And so this graph is a mesh simplification result. You can see, so the line just means this point will be mapped to this point on these two surfaces, and they are going to be correspondence for our further analysis. And yeah, for registration, we apply the coherent point drift method, and the details can be seen in this paper. And we want to say that based on previously match simplification, it's become much more efficient to do the registration. I will show a table. Yeah, here's the table. So you can see with when we do not do the simplification, so there's going to be about average, generally it's going to be about 50,000 of points in each surface. And it's going to take hours for us to do the registration process, and it's not acceptable. Yeah. And if we do the simplification, so in this case, we just keep about 10% of the original points on the surface and try to keep the shape as real as possible. And in this case, it's only take minutes to do the registration. And we think that is good. And yeah, you can see this time just decreased dramatically. And so the third part of our framework is local feature computation. Actually, we include we tried lots of local features from differential geometry, and we want to introduce 3 in our framework. That is 3-dimensional curvature, normal vectors, and surface area. So I just want to mention that in 2-dimensional space, we can compute the curvature for a curve, and generally it's like curvature means if a curve is more curved, then this value is going to be larger. And when it comes to the 3-dimensional space, since it becomes more complicated, so we have different kind of definition for curvature as these 4. We have maximal principal curvature, minimal principal curvature, Gaussian curvature, and mean curvature. So let me introduce the visualization result for 3-dimensional curvature at first. So here is a visualization result of different kinds of curvature, and actually we use our defined force color function to visualize the result on these registered surface pairs. And in each graph, we can see actually the blue color means lower value of curvature, while the right color means higher value of curvature. And you can see here, if the tip of the nose and the ears, there's more red color because this part of the head is more curved. And generally, you can see the front head, this part is flat, so the curvature value is smaller. And yeah, this is what we expected from the definition of differential geometry. So yeah, here's the interesting thing. We do the comparison based on the registration as we have introduced before. So and we visualize the result on the pre-surgery surface. So as I mentioned that for each point on the pre-surgery surface, we can find the corresponding points on the post-surgery surface. So, and as we already compute the local features of 3-dimensional curvature for each of these surfaces, we can compare those 2 values. And yeah, we use a kind of complicated mathematical formula to represent this kind of computation. You can see the details in our paper. But here I just want to mention that in this visualization result, the right part means there's more change in this part of the head, and while the red value means it keeps quite well. So in general, and for this patient, we want to say that this patient, the surgery is done on the front head. So you can see this part, there's small red value, and this is what we are expecting. So next measurement is normal vector. So based on normal vector, we define a measurement to measure how the head is symmetric or not. So generally speaking, we have more complicated formula in our paper, but generally speaking, when the absolute value of this measurement is small, that means the That means the head is more symmetric. And yeah, and you can see from this 5 patient, we can see that the absolutely value is going to be absolutely value of this measurement is kind of become smaller, and which means the surgery just make the baby's head more symmetric. And the last thing about I want to introduce is the surface area. So for surface area, it's a little bit complicated, but we used previously, you can see this from this image, we already have the comparison based on curvature. So to consider the surface area, we use, for each point we have on the pre-surgery surface, we already have a value of that comparison, right? And then we just try to use a threshold to filter some points. That means, so if the difference on this curvature comparison result is smaller than the threshold, we're taking this kind of points as they do not change obviously. So we don't consider the area near this kind of point. And for other points, we're going to consider the area near the points that is larger than the threshold. So, and then we just add all of such the area near such kind of points all together, and finally we take this value divided by the total area surface. So in this case, all of the value is going to be lay in the range between 0 and 1. So that means it can be compared between different patients, and that is very important. And actually, since we have 4 different kinds of curvature, we apply the comparison result of 4 different curvature in this experiment. So you can see we have maximal principal curvature, minimal principal curvature, mean curvature, and Gaussian curvature on this experiment. And yeah, and actually we tried different threshold. In this case, the threshold is a quarter, and in this case, the threshold is 0.5, and in this case, the threshold is 3/4. So I just want to mention that from the doctor's view, this kind of measurements is informative because it describes how dramatically the baby's head just changed. Okay. Finally, let's give a little summary about our framework. So in this paper, we give a kind of objective evaluation system, and we also select some useful local features from differential geometry, and we apply this kind of techniques to help the physicians to assess the quality of the plastic surgery outcomes. And I just want to mention again, we don't depend on any ground truth from the doctor's opinion. So it's going to be totally automatic and objective. So in the future, I think we may try a few interesting things. So we would like to generate a group of normal template based on different age, different gender, and different race. And we're going to apply the similar measurement between the surface pair of the pre-surgery head shape and the normal control, and the post-surgery surface and the control. And we can say if the difference is going to be smaller. If this is smaller, then we think this baby's head just grew more normal, and it's in the right approach. So, any questions? Thank you.